Hi everybody, I'm Mr. Spudik, and today we're talking about falling objects and gravity. Alright, so let's get started. Of all the scientists that are going to help us with gravity, the first one that really had a lot of significance is Galileo. Okay, so Galileo is going to be one that kind of starts to break down this concept of gravity a little bit better. So if you think about it with gravity, people before Galileo knew that objects would fall. All right, they all saw that. And people also knew that objects would fall and speed up as they fell. So think about it this way, right? If you were able to drop a pebble, I got a tennis ball. If I drop a tennis ball right here, okay, it'll be pretty easy to catch. It wouldn't hurt my hand. I wouldn't notice much, right? But what if I had somebody drop this tennis ball from the top of a roof of a building? Well, we know that the tennis ball will be a lot harder to catch. Okay, it would hurt a lot more when I catch it. So people knew that. People knew that objects would speed up when you have them falling. But Galileo is going to be the first to really break down how much does it speed up. Okay, and the way he did that was he had a ramp. Okay, and the ramp he would set it to different angles. And, you know, if he had just dropped something and tried to measure the distance as they fell straight down, it would have been a lot harder for him to break things down. But with a ramp, he was able to change the angles and see, you know, a really low angle, what was going to happen, and break it down easily. And then he could change that angle and see what happened. Well, if I went at a higher angle, what would happen? Okay. But the ramp, the whole idea was this. He would have that ball roll down the ramp. Okay. And he didn't have a stopwatch, right? It wasn't like he could take out his phone and start up a stopwatch to time things. What he had was a metronome. Okay, anyone that's played music knows a metronome. It just goes back and forth with equal times. Okay, so he had this metronome going back and forth. And so he let the ball travel down, and he saw how far it would travel after 1 second. Okay, and then he let it travel and see how far it would go after 2 seconds. And then 3 seconds, and then 4 seconds. Okay? Now, the distances are not exactly important right now. We don't need to know the exact distances they fell, because every time he changed the angle, the distances, right, at 1 second, the distance would be some distance, and if you change the angle, it would be a bigger distance. But the key thing is he wanted to compare. He had to compare the distances. So after 1 second, he measured that distance. Okay, after 2 seconds, 3 seconds, and so on, he had to measure those distances. Okay, so what he found out was this. He measured the distance from 0 to 1 second. Okay, and whatever distance that is, let's just say that's 1x. Okay, that's our distance. It was 1x right there. When he measured the distance between 1 second and 2 seconds, he knew that it was going to be further apart, but he didn't know by how much. But when he measured that and he compared the distance from 1 second to 2 seconds, he found out that that distance was 3 times the length it was between 0 and 1 second. Okay? So then he went between 2 and 3 seconds, and he measured that distance. All right? And what he found out was that distance between 2 and 3 seconds was 5 times the length that it was between 0 and 1 second. Okay, I'm going to pause here in a second, but I want you to guess. Can you guess what the distance was going to be between 3 and 4 seconds compared to the distance it was between 0 and 1 second? Pause it here and guess. Okay, are we done? Did you guess that it was 7 times? So the distance from 3 to 4 seconds was 7 times the length that you would see between the distance from 0 to 1 seconds. So, how can we put that into fancy science words to make ourselves sound smart? Well, Galileo figured out that the distances between time intervals, 0 to 1, 1 to 2, 2 to 3, 3 to 4, the distances in between those time intervals matched a sequence of odd numbers. 1, 3, 5, 7, 9, whatever. Okay, so he found this pattern. Okay, and it doesn't matter what the distance was. And of course, he could then have something fall straight down, and it would mean the same thing. Whatever it would fall after 1 second, that distance, the distance that you'd get from 1 to 2 seconds, would be 3 times that length of the original. Okay? All right. So what about total distance? So then Galileo measured total distance. And Galileo said, all right, well, from 0 to 1, again, my distance is 1x, whatever that distance is. Okay? But then he went total distance from 0 to 2 seconds. And you can do the addition here too, right? But what he found out was the distance from 0 to 2 seconds would be 4x, 4 times the length of what it was after 1 second. All right? And then he went from 0 to 3 seconds. Okay? And from 0 to 3 seconds, you can just add 4 plus 5. But for 3 seconds, he would get a distance of 9 times the original distance. All right? So let's go 0 to 4. 0 to 4 seconds. He got a distance of 16. So the distance from 0 to 4 seconds was 16 times the length than it was from 0 to 1 second, whatever that length was. Okay? So I want you to now think about the numbers. With 1 second, we got 1 times the length, obviously. With 2 seconds, we got 4 times the length. With 3 seconds, we got 9 times the length. And with 4 seconds, we got 16 times the length. All right, think about the math in here. Can you guess what the relationship is between the time and the total distance? What number? Do we see a number pattern going on here? I'll pause here and you can guess. Okay. Did you guess that it's going to be squared? Right? 1 squared is 1. 2 squared is 4. 3 squared is 9. And 4 squared is 16. So the next thing we could say is Galileo found a relationship between the total distance fallen and the time squared. Okay? All right. Moving on to the next thing. So now let's kind of summarize what he figured out with these experiments. He figured out that there was some velocity, or to figure out the velocity when something was in the air. At any point in time, there was some type of constant, some constant number, and if you multiply that times the time that it had been falling for, you would know the exact velocity when it was falling. Okay? The other thing was so then we have our summary from the experiment. The distance between integers, okay, or the distance between the time intervals follows a sequence of odd numbers. Okay, 0 to 1, 1 to 2, 2 to 3 seconds. You would have one distance would be whatever it is, 1. Okay, 1 to 2 seconds would be 3 times as much, then 5 times as much, then 7 times as much, and so on and so forth. Okay, and then the total distance follows and is going to be related to the square of the time in the air. Okay, 1 squared, 1. Okay, whatever that distance was. 2 squared, that distance would be 4 times the length it was after 1 second, and so on and so forth. Okay? All right, now, when you do your equations, I talk about the big 3 equations, and if you watch my video from before, I give the big 3 equations to use. But whatever equations you have, they're the same equations for objects falling as they were for going horizontally. And in fact, it's even going to be easier because we will always know a new number to always put in our list of givens. Okay? So, a couple other notes about gravity. 1, gravity is an acceleration. It's not so much a force as an acceleration. So you can think of it in some ways that if an object falls, after every second, you could add a 9.8 meters per second to that falling downward velocity. Okay? Because it's just that it's going to keep speeding up and speeding up and speeding up. So it constantly is accelerating. And it's accelerating at the number, and again, this number is negative 9.8 meters per second squared. So acceleration is negative 9.8 meters per second squared. You'll see it so often It's used so often, and we're always talking about gravity, that some textbooks and some problems might even have acceleration listed as little g. Okay, so little g is not just my rap name. Little g also means negative 9.8 meters per second squared. Now, you could talk to your teacher. If your teacher wants you to always write it as a negative, some teachers won't mind and want to have you write it as positive, but gravity will always be 9.8 meters per second squared down. Okay? All right. Now, remember this, and you've probably heard this before, but mass does not affect how something falls. So, when Galileo was doing this experiment and Galileo was talking about gravity, he said, gravity, let's say I had a feather and I had a hammer and I tried to drop the two of them at the same time, but I got rid of all the air. So let's say that I had a feather and a hammer and I dropped it somewhere where there was no air. The feather and the hammer would hit the ground at the exact same time. Does that make sense? So the feather and the hammer, it's not the mass that has those fall differently here on Earth. It's the fact that the feather has air resistance to it, and the hammer does not. So if you went somewhere else where there's no air, those two objects would hit the ground at the exact same time. All right, astronauts, when they first made it to the moon, okay, with the Apollo 11 mission, when they made it to the moon, astronauts actually did Galileo's experiment. They said, hey, let's see if he's right. And so they took out a feather and the hammer, and they dropped the feather and the hammer on the moon, and because there's no air, the feather and the hammer hit the ground at the exact same time. Okay? All right, so here's my experiment. Another way of thinking of it. I have two sheets of paper. These two sheets of paper have the same exact mass, right? These two sheets of paper still have the same exact mass. The crumpled up piece of paper fell faster because it didn't have the same air resistance. So it wasn't the mass that caused one to fall faster. It was air resistance. Okay? All right. Now, I will tell you this, though. After saying that, in a normal physics class, we will not be touching upon too much air resistance. So there might be an experiment here or there where you need to think about it. But for the most part, when we talk about things going through the air, we're going to talk about a rock, okay, or a ball, or something that doesn't really have much air resistance to it, or not enough that we'd notice it. So you won't have to worry about taking into account air resistance when things fly into the air in this class. When you do an AP physics course, then you could start thinking about air resistance, but not so much here. All right, a quick reminder that you will be using the same equations that you've been given before. So it doesn't matter, whatever the horizontal motion is, whatever those equations were that you were given, it's going to be the same equations for things falling, except you will always know gravity, so you will always know the acceleration. On Earth, gravity doesn't change, so the acceleration will always be negative 9.8. All right, that's it for me. Thanks for watching, and I'll talk to you later.